So conics is, of course, a very old subject, going back to the Greek mathematician. Immense literature on various properties of conics. I'm going to present to you 3 different definitions of it. They've all their own interest, and we'll see how they're related to each other. But we should also ask ourselves, why do we study conics in the first place? And we'll get to that in a second. I mean, of course, it's a neat set of objects, a neat set of curves and all that, plenty of nice properties. But is there a fundamental reason why, at the mathematical side, it's both important and interesting? Okay? So, first definition of conics is the one that you've probably seen in various occasions before, which is that conics are the sections of a cone. So, first thing to know is that in mathematics, this is a cone. In normal parlance, that would be called a double cone, right? Because if you take a cone of ice cream, you don't expect to have both sides. But in mathematics, the object that makes sense, the cone has both sides. Okay, so be careful. Sometimes it says a double cone, but mathematics, we just say this is a cone. And we take a section of the cone with a plane. Okay, so last week I spent some time playing with a 3D printer. And rather than doing explicitly, I brought you a set of different conics. We have the real 3D one, and you can section it with a plane that's perpendicular to the main axis. That makes a circle. If you change the inclination, and I can do that here at the same time, I thought that was better than trying to do it here. Oh, no, that's not this one. I changed this one. So here is my plane, you see from inside. So here is the circle. Now if I change the inclination of this plane, not too much, and you see what we get is an ellipse. Or is it? We don't know yet. We still have to establish that. Okay? Part of the exercise today is to show that these are indeed circle, as we expect. And the next one is an ellipse. So that would be this one. Now, if I keep going with the angle, there is a critical case, so here, where that plane is going to be exactly parallel to, let me rotate that a little bit. Okay, so that you see the plane now is parallel to the axis of the cone, or to the side of the cone. So that's, I'm going to put that back here. So that would be, you see that in this case, this side is parallel to this one, right, to the axis. And that will show is a parabola. And then if you keep going, it was a little hard to print a double cone, as you can imagine. So if you keep going, you get this. And if it's not clear what it is, let's get rid of the cone, and you see that what we get is a hyperbola, 2 sides of the hyperbola. Okay, so depending on the inclination, we get the limit case with the parabola, and then we get the ellipse, and then we get a circle. Right, and then we can put it back. So that's the first definition. I thought that I'll bring even a bigger cone, which I steal from my kit. It's a flashlight. This is what people use in the dark before the invention of the smartphone. Okay. Oh, look. I need the light for that. So the flashlight makes a huge cone. Woohoo. So let's see. Well, there is a little bit of diffraction. But if you look at the envelope of this cone, as I did early on, yeah, that should be about this. Right? So if you look at the envelope between dark and light, you get this one. Now, parabola is very hard to do because it's very hard to distinguish on a short segment the difference within hyperbola and a parabola. But here I'm sure that it's a hyperbola because my cone is along the vertical axis. My cone is along the vertical axis, and the plane of the board is the section of the cone. So that makes a huge cone of light. Okay, now let's see if I can do this again. Okay, so here is an ellipse, and you see the light here is at what we'll call the focus. And of course, the easy one is the circle, which is just the intersection with the plane, which is nothing but a particular case of an ellipse, of course, as we'll see. Okay? So that's the first description of conics, but it's not quite satisfactory. Let's see, default. Why? It's certainly the historical one, and that's how it's all started. But in order to define conics here, you need to define a three-dimensional object, so in a higher dimensional space, then take a section with a plane, find the intersection, and that's what defines the object. Why would we need to go to 3 dimensions to define 2-dimensional object? Right? Typically, we want to have a definition that's purely in the same space. So the second definition is as a set of points. So this is the kind of problem that were very popular for thousands of years. Define conditional constraint as on points in the plane and try to find a geometric set that satisfy them. So these are usually described as finding locus of points. Now here is a problem. Do we say loci of loci? Any opinion about that? If you're classicist, you learn that in Latin the C is always a hard C, locus, so it should be loci. But in English, you soften the C to make loci, like foci, and so on. Okay, so to me it sounds a little bit better with loci. So who prefer loci and who prefer? Okay, let's vote. Who is for loci? Who is for loci? Okay, very good. Loci? No? Okay. Okay, so we'll call it loci. So, these are the typical question. So, given a line D, which we call the directrix, beautiful names, all problems. A point F, called the focus, foci, when there is more than one, and a real number, E positive, that we call the eccentricity. Find all points P such that the distance PF is a multiple by E of the distance PD. Okay, so we have a line D in the plane. We pick an arbitrary point, F, focus, and we look at all the point P. So we look at the distance between P and D, so that's distance PD times E, and that's PF. Oh, sorry, that's not E, that's just the distance, PF. And the question is to find all the points that satisfy this, depending on E and the distance to the line between F and between the directrix and the focus. So that's the second type. So here I have exactly that condition. I solve that condition numerically, where I have a parametrization, but we'll get to that. And you see that as I change the E, I get either ellipse, I get the critical value at 1, which we'll see is a parabola, and after that I get the hyperbolas. Okay? Here I have another factor here, which is called the semilatus rectum, which is a way to change the parametrization. Just in case you wonder, this is the distance between a focus, it's the normal distance between a focus along the axis of the conic and the conic itself, a point on the conic. Okay, so that's the second definition, which is nice because it's purely geometric, right? There is no 3D or anything like that. It's not either fully satisfactory to me because why? Why this one? Why don't we say, oh, let's take all the points so that is the sum of two distances or the square of one or something like that? What's special about this one besides the fact that it's a way to recover all conics? We still don't know what's special about conics. Of course, we know from other fields like astronomy, Kepler's law, the two-body problem, that the solution of the two-body problems are all conics. So we know that conics are important in science, but why do we study them in mathematics? Okay, so the answer, or partly of the answer, is the third one, which is an algebraic view of the same type of problem. See, where we consider the most general polynomial of degree 2 in two variables. Plus E y plus f equals 0. And then it starts making sense. Why? Because all we've done before essentially has to try to describe the set that are linear set, polynomial of degree 1. Right? We look at intersection of sets in the plane and higher dimension of polynomial of degree 1, linear function. And here is the first generalization to nonlinear function. Right? This is the most general second order quadratic function in two variables. And the question is, describe the possible solution of this guy. Okay, the three are not completely equivalent, and we have to be careful. So the third part, so the third as quadratic functional, it says I give myself a quadratic functional, and I find a set of points x and y that satisfy that. Right? So here I have different one. For instance, I have this one, which is essentially x squared plus y squared times a constant equals 1. And when I change that constant, I can change. Okay, I have this one, which give me hyperbolas. And you see these are all special case of that. And all I do in this case is give that function and ask Mathematica to find all the x and y such that it's 0. So it's not doing anything else. It's trying to describe the set of function or the set of points in the plane that satisfy this equation. So it's the first time we really do something truly nonlinear, right? And as soon as you do that, everything is more complicated. Because when it's linear, everything's fine. It's all you can all reduce that to matrices and problem with matrices, inverse, transpose, and all that. But when it's nonlinear, everything becomes much, much more difficult. So we have three different definitions of apparently the same object. Another question is to see if they're equivalent with each other. But before we do that, let's start with number 2, the set of points, the loci, supposedly, according to you. and try to try to see what sets of points we can obtain doing that. So in this case, so we have 2. So we look at PF equals EPD. Let me put this time D like this. And I'm going to put coordinate x tilde, y tilde. And I'm going to put the focus here. So that's PF, and that's PD. So now the name of the game will be to start with this definition and try to reduce that to change variable, so that in new variable x tilde and y tilde, we have normal forms. We have normal forms for the different conics. And the normal forms are either x squared over a squared plus y squared over b squared equals 1. And you see that directly this is a generalization of circle when a equals b. So you change one axis versus the other one, so that's why you make ellipses. So that's the first possibility. So it's this one. If you change one of the sign, you get x squared over a squared minus y squared over b squared equals 1. And the other possibility, that's not quite a limit of any of these, is the one in between, which is y squared equals 4ax. Okay? And so these are ellipses, hyperbolas, and parabolas. So in order to capture them, we have to start from the definition, the geometric definition, and show, essentially find a change of variable between x tilde, y tilde, and x and y that brings that to these different forms. So that's what we're going to spend a little bit of time doing now. And we're going to separate that in multiple cases. Let's call that 1. Let's call that 2 and 3. OK. So for 1, we're going to assume that the eccentricity is between 0 and 1. So the point P has coordinate x tilde, y tilde. And so the distance PF is square root of x tilde square plus y tilde square. And the distance PD is just k minus x tilde, where k is this distance here. Right. So yeah, it's k minus x tilde. So if I write the condition that PF equals EPD, I obtain square root of x tilde square plus y tilde square equals E times k minus x tilde. I take the square of that to obtain x square tilde plus y square tilde equals E square k minus x tilde square. Okay, now I can rewrite that as an expression. I can just rewrite that as 1 minus e squared times x tilde square plus 2 e squared kx tilde plus y tilde square. And then I still have the e square k square on the other side. Okay, we got to come back to t's, so let's give it a name, star. Okay, so remember, we have t's in terms of x tilde, and we wanted to have a simple form just with squares, x squared plus y squared. So we're going to do today a lot of it, which is complete the square. We're just going to rewrite something as a square plus something as a square equals something. Okay, so that's the kind of exercise you've done in school. So what I do is I want to rewrite that as x plus x tilde plus something square plus y square, and then have the extra bit. So I can rewrite that as 1 minus e squared times x tilde plus e squared k over 1 minus e squared, and that's square. So that's take care of these two first term, but I've added one extra one, so I have to take care of that. So it's e squared k squared so I have to remove it, so I had it here. So it's plus e4 k squared divided by, it's 1 minus e squared square, but I multiply again on this side, so I obtain this one, which I rewrite it as e squared kappa square times 1 minus e square, so the e4 disappear. The algebra is beautiful because it all works out. I might need it. And so T is the eccentricity, and all that works out very nicely. And now I'm really done here, because if I want to make it look like this guy here and find A and B, all I have to do, all I have to do is define this as a new variable x. Well, not quite, yeah, x. Define this as the variable y, and then divide everything to get A and B, right? So I have defined x equals x tilde plus e squared k over 1 minus e squared. Y tilde equals y. To obtain 1 minus e squared x squared plus y squared equals e squared k squared 1 minus e squared. Okay, I'm going to come back to this one. So let's call it double star. Now, e is between 0 and 1 in our case, so I'll be able to divide. So if I divide by e squared k squared multiplied by 1 minus e squared. So I have 1 minus e squared square, and I define A to be k times e over square root of 1 minus e squared. I can take, oh no, 1 minus e squared, sorry, and b as ke, which is just the square root of this term, 1 minus e squared, I obtain x squared over a squared plus y squared over b squared equals 1. And that's the normal form of the ellipse. And now we have the relation between the semi-axis A and B and the eccentricity and the distance to the directrix. So in terms of drawing, what is A and B? Where you see that when y equals 0, x squared or a squared equals 1, so x equals plus or minus 1. So I have the focus here F. I have A and minus F and minus A. And I have B here, B at minus B. And so my ellipse goes around. Something like that, with the directrix being here, or there is one on the other side too that you can create by symmetry. And this is with respect to x and y. Okay, so conclusion of number 1 is that the set of points that satisfy this identity here, when e is between 0 and 1, is an ellipse. We still have a little bit of a problem, where it's not a problem. So the directrix here is x. So x equals a over E. That's where the directrix is. And the focus here is E times A. What about the circle? It's always important to look at particular case and make sure that they work, or limit case. Do we have the circle in this family? Well, when I write it 1 minus e squared times x squared plus y squared equals e squared k squared over 1 minus e squared. So the question now is, what about circles? Well, it's not in this family, because you see that in this family we would need A to be equals to B to have a circle. But A equals to B means that 1 minus e squared equals square root of 1 minus e squared. So that means that E must be 0. Right? And that family is defined for E between 0 and 1. So here, same thing here. If you look at here, we really like to take where we know that a circle is x squared plus y squared equals r squared, right? So we really need this to be equals to that term. So 1 minus e squared equals 1. So E must be 0. Aha, but if E is 0, this is 0. And that's a very small square. It's a point. It's x squared plus y squared equals 0. Okay, but we can do something a little bit different, because we can still play with k. So what we want is that we want to take the limit for e going to 0 and enforce that in that case e squared k squared goes to r squared. So we take a limit where k, so k, we take k to be r over e. And in that case, a limit of e going to 0 of that expression gives x squared plus y squared equals 1. Okay, oh, r squared, sorry, the circle. So it's a little surprisingly difficult to get the circle, because what you must take is fix r and take e to 0. So you have to take k going to infinity. So you push the directrix away to infinity. OK, so that's taken care of. Now 2, what about hyperbolas? So I'm going to start from the same expression, star. So that's because up to this point I've made no assumption on E. So hyperbolas, as you saw from the obtained for E bigger than 1. In this case, this is less than 0. And this is also less than 0. So you can go to exactly the same step of defining A and B. At this time, I define A to be ke over e squared minus 1. Change the sign so that the first term is positive. And B equals ke over square root of e squared minus 1. To obtain x squared over a squared minus y squared over b squared equals 1. I want to come back quickly here, say that from there is a very nice simple parametrization in terms of the angle with respect to the origin, which is x equals a sine t, y equals b sine t, b cosine t. With t in 0 to pi. Or you can go the other way, of course. So in the same way, we can parameterize the ellipses with trigonometric function. We can parameterize the hyperbolas with hyperbolic function. I'll get back to that in a second. Let's look at the geometry. Now, what you can see from this expression here is when x is very large, 1 with fixed a and b, 1 is very small compared to x and y, right? That means that essentially the solution of this equation is going to get closer and closer to x squared over a squared equals y squared over b squared. And that is 2 lines in the plane. So for very large value of x and y, the hyperbolas is going to get closer to these lines, so which are the asymptotic lines. So let's put that here. So this is ay equals bx, and that's ay equals minus bx, the 2 solutions of this equation. And again, it goes to a and b, to a and to minus a. And so the hyperbola becomes asymptotic to So I don't know if you ever thought or realized the nice symmetry that there is between ellipses, for which we use sine and cos, and hyperbolas, for which we could sinh and cos. Yes?
Shouldn't x be the cosine, the hyperbolic function?
Well, that depends where you put your t, right? If you want the t to be this angle here, then it's the cosine. If you want to be the complementary angle, it's the sine. That's why I left it. I left it to the reader to place the right t. But yes, you're right. If I have a point here, the angle is this one, right? It doesn't matter. It's a parametrization. You can shift it by pi over 2, and you get the cos and sine. OK, more interesting is that parallel between sine and cos and sinh and cos. These are very nice. One is elliptical, the other hyperbolic. And you might have seen already, or you've seen in detail, you can define these, of course, the sinh and the cos, the hyperbolic sine and cos are defined to exponential, and the sine and cos are defined as sum of exponential of imaginary value, e to the ix plus or minus e to the minus x over 2i. Okay? So these are very, very similar. Right? And it is that kind of reflection or structure that led people to try to further generalize this concept. If you think of sine and cos, these are periodic function over the real line. If you think of sinh and cos, they are periodic function over the imaginary line, if you think them in terms of imaginary number. And it's by manipulating this object that in the 19th century people started looking at function of complex variable z to complex valued. And there is a very nice generalization of the concept of function that are periodic in x, or periodic in imaginary direction, periodic in the real direction, to the set of all functions that are periodic in both directions, or there are two directions in which they're periodic. And that led to the whole discovery, or invention, as you wish, of elliptic function. It's a huge branch of complex function theory, that the set of functions that are doubly periodic in the complex plane, which take these two cases a particular limit where one of the period goes to 0. So what is simple object, and are interesting because they're the first nonlinear object, also led to much more interesting mathematics, or newer mathematics, when people were looking at them. For instance, a simple question is, what is the length along the arc length from this point to an arbitrary point? Well, we know for the circle that it's very simple. It's the angle times the radius. Right? And the answer for the ellipses is actually very complicated, because these integrals, or computing the arc length, cannot be done exactly. And again, that led to a whole new topic in mathematics, which are elliptic integrals, a whole set that have these beautiful properties that pops up everywhere. So even naive questions like these lead to very interesting mathematics. OK, there is still one case we have to do. I don't think I'll need that, so. Let's make space here. So we've done the hyperbolas. That's all good. One more point here is that the directress here is, you can check, is at A over E. Right, from this relation. Okay, so number 3, parabola. So again, we go back to well, now I'm going to go back. Sorry, here that was double star. Let's go back here to star. So that's before we completed the square. You see, we can only complete the square if e is different than 1. So now the parabola is the last case to look is e equals 1. So we have to go back in our computation before we made that assumption. And in that case, it's 1 minus e square x tilde square plus 2e square k x tilde plus y tilde square equals e square k square. So if e equals 1, t the first term disappear, and I have 2k x tilde plus y tilde square equals e square k square. Again, I introduce a to be k over 2. Oh, there is no e here. And I make a change of variable x equals a minus x tilde, y equals y tilde, and you obtain y square equals 4ax. In that case, so it's a nice form. You said, oh, this 4 is a little bit annoying. I would rather not have the 4 there, right? It'd be nicer algebraically if it was y square equals ax, but there is a good reason for that, is that the a is not the focus of the parabola. Actually, the directories is over there. So just to recap here, what we've done is to show that this condition with e bigger than 0 lead to different cases, leads to the 3 main cases that leads to the normal form of the conics. So it's one definition that encompasses all the possible conics and lead to the definition in terms of geometric object. Now, what we're going to do next time, a little bit of a preview, is the comparison between number 1 and number 2. If I take a cone in the plane, if I take a cone and slice it with a plane, do I obtain all the sections that I've found, all the conics? Okay, so the next question is to go from 1 to 2. And in order to do that, what we'll do is we're going to take a plane that goes to a particular point here. So alpha and theta, and we're going to find the intersection explicitly. So we have to compute that. It takes a little bit of algebra, but then we'll see the exact correspondence. And then we'll finish by showing the third part, which is that the set of all these functions is actually bigger than the conics. It has a few more cases. But is a contains all the possible conics. So there is a particular case also that I've not mentioned directly here. If I take a plane that is perpendicular to the cone, contains the axis of the cone, then the slice of the cone gives me two lines. And that's, again, it's just like the circle. It's a limit case of the hyperbola that you can obtain. So actually, if I wanted to show you another reason we study conics, which is they have cool properties. And as long as my laptop here, I thought it'd be nice to show you. So if you think in terms of light ray, Snell's law tells you that the angle of incidence equals the angle of refraction. So that means if you have a curve and you look at the normal and the light ray that comes to this point, if this curve was a mirror, the angle of incidence is this one and the angle of refraction is this one. And according to Snell's law, the two are the same. Incidence equals reflection. Okay, so what we can do is throw rays at his conics and see what happens. And this is one of the nice properties, of course, of conics, is that here is the source of light, that's my point. Let's make the ray a little bit longer. And you see that if I don't choose well the point where I start, then the ray all scattered. But if I put my light, my flashlight, exactly at the center, then the light ray go up, and then they reflect all parallel to the axis. That's one particular property of the parabola. And this is why we have parabolic dish. This is why the headlights for cars used to be made of parabola, with a light inside that reflect to the parabola to make a straight beam of light. Now, what happens for the ellipses is also very neat. So we can play the same game with ellipses. So if I take a point anywhere, you see I have a reflection everywhere, and it's quite scattered. This is what happens when you play. Essentially, you play pool, you play billiard inside an elliptical table, right? But if you choose your point well at the focus, or one of the foci, this is what happened. All the points go, so I have to make it just there. So all the light rays end up at the other focus. That's a very neat properties, right? And that's one property that you can exploit if you want to spy on people or want to eavesdrop. You can make a parabolic echo chamber, so that if you are sitting at F and talk, and the sound wave propagate more or less with the same rule, then they all coincide, they all focus on the other focus. And there is a good example of that, which is the statuary room in the US Capitol. It's this mostly elliptical dome. It used to be the place where representatives would meet in the old days. So in the 19th century, John Quincy Adams would go there and eavesdrop on his opponent by placing himself at the right point to hear what other people would say. And he liked it so much, he was president at the time. 20 years later, he actually died of a stroke in that room. Or he had a stroke in that room and died 2 days later in the 1840s. But that's for you, conics into action. Okay, that's all for it, and we'll finish conics tomorrow. Thank you.